Okay everybody, this is going to be the first lecture video for Chem 1212. Now the first new information we're going to cover comes out of chapter 11 in your book, which is liquids and phase changes. But first you might be wondering what you need to carry over from Chem 1211. I know it's fairly common for people to not take these classes in back-to-back semesters, so for everyone, but especially those people, I want to briefly take some time to address that. So what should you have a good grasp on from Chem 1211? The answer, in brief, is yes. We can be a bit more specific about what to really focus on, though. First of all, stoichiometry is really important to have a handle on in this class, and that's especially true for molarity. Stoichiometry is featured in Chapter 3 and 4 of your book, and molarity specifically is covered in Chapter 4. It's also really important that you know the ins and outs of ionic compounds, how to determine the formula of an ionic compound, what typical charges are on common elements, polyatomic ions, etc. You can find these topics covered in Chapter 2 and also in Chapter 6 of your textbook. We'll be doing a lot of deriving, balancing, and classifying net ionic equations later on, although it'll be a few weeks before we really start diving into that in this class. You can find information on these topics in Chapter 4. The other main thing to focus on is thermochemistry, which is in Chapter 9 of your book. Oh, and besides thermochemistry, in this chapter we'll be referring often to intermolecular forces. I covered this topic in my Chem 1211 course, but it's possible that you may not have. And whether you've come across intermolecular forces before, or if you have but you want a refresher, you can look back to Chapter 8 in your book. I could also post my Chem 1211 video about intermolecular forces if anyone would find that helpful. I'd be happy to provide more direction and give you example problems to work on any of those topics if you want. Anyway, let's get into liquids. As you probably already know, there are three main states or phases of matter: solids, liquids, and gases. There are other phases, and we'll actually talk a little bit more about that at the end of this chapter, but those three are the main ones. A liquid is a phase of matter that you probably already have some intuition about. To give a formal definition, we can say that it's a condensed phase of matter that takes the shape of its container and is capable of flowing. There's two other properties that I want to introduce here: viscosity and surface tension. Viscosity refers to the resistance of a liquid to flow. To get an idea of viscosity, just imagine pouring something like maple syrup or molasses out of a jar. It flows out very slowly compared to, say, a jar of water, because the syrup or molasses has a very high viscosity compared to that of water. Surface tension is another property of liquids that has to do with their resistance to spreading out and increasing their surface area. Some animals, mainly certain types of insects, can take advantage of the surface tension of water to walk across its surface. If there was no surface tension on water, they wouldn't be able to straddle the surface and they would just sink. This table shows some common liquids and their viscosity and surface tension at 20 degrees Celsius. These values aren't here for you to memorize, or even for us to do any calculations with, but we can observe some trends that illustrate what underlies the phenomena of surface tension and viscosity. The first two liquids in this chart are pentane and benzene. Like virtually all compounds of carbon and hydrogen, known as hydrocarbons, they are nonpolar, and in this case they're liquids. The only intermolecular forces present between the molecules in these liquids are relatively weak London dispersion forces. Compare that to water, glycerol, or ethanol, also seen in this table. These liquids have comparatively higher viscosities and surface tensions, and you can probably tell from the formulae that they contain oxygen-hydrogen covalent bonds. That means that they're going to be polar molecules, and even more importantly, that hydrogen bonding intermolecular forces exist between molecules in these liquids. Hence, the IMFs between molecules in these substances are much higher than they are for pentane or benzene. Hence, there's a pretty clear association here. Stronger intermolecular forces give rise to higher viscosities and surface tensions in liquids due to stronger interactions between the molecules. Let's take a look at another property of liquids: vapor pressure. You've probably noticed that if you leave a glass of water out for an extended period of time, it starts to slowly evaporate and the liquid level in the glass will slowly decrease. Why does this happen? The answer is that water, like any other liquid, has a certain vapor pressure or partial pressure of gas in equilibrium with the liquid at any given temperature. Put another way, there's an equilibrium pressure of water vapor above the liquid, which varies with temperature. Going back to the example of a glass of water, we can see a practical effect of this. Evaporation, you may have noticed, takes place much more slowly in higher humidity. This is because there's more water vapor in the air to maintain equilibrium with the liquid. The vapor pressure of a liquid is positively correlated with its temperature, and this graph explains why exactly this is. The kinetic energy of molecules in a liquid, just like in a gas, are distributed across a wide range of values. Of course, the average kinetic energy of the molecules in a higher temperature or hotter liquid will be higher than the average kinetic energy of molecules in a liquid at a lower temperature. Generally speaking, any liquid molecules below a certain energy threshold, represented on the graph by the vertical dotted line, are trapped within the liquid. Any molecules with higher kinetic energy than this, however, will be moving fast enough that they can escape the liquid and move into the gas or the vapor phase. As we can see, the number of molecules in the higher temperature liquid above this energy threshold, which are represented by the red shaded region, are greater than the number of molecules above this threshold in the low temperature liquid, which is represented by the blue shaded region. Those graphs give a good qualitative explanation for the relationship between vapor pressure and temperature, but can we quantify this relationship? The answer, of course, is yes, and for this we can use the Clausius-Clapeyron equation. The equation on the top of the slide shows us the nature of the relationship between these two factors. On the left side of the equation, we have the natural logarithm of the vapor pressure. It's equal to negative delta H vape, or the enthalpy of vaporization, divided by the molar gas constant R, times 1 divided by the temperature, plus a constant C. Let's unpack what this means. First, the enthalpy of vaporization is a value that depends on the particular liquid, and it's typically expressed in units of kilojoules per mole, like any other enthalpy change. R is the same constant from the ideal gas law, but it's expressed in a different set of units, and so it has a different value from what you're used to from the ideal gas equation. But it's still a constant, and it has the particular value of 8.314 joules per mole per Kelvin. This never changes. Of course, when you divide delta H by R, keep in mind the units. You'll either need to convert delta H to joules per mole or R to kilojoules per mole per Kelvin. T is the temperature in Kelvin, never in degrees Celsius. Finally, C is a constant that depends on the liquid and the units used to express the pressure. Generally, it's determined by making a regression line and finding the y-intercept based on a number of data points. There's an alternative version of this equation shown on the bottom of the screen. This version is most useful if you want to use the known vapor pressure of a liquid at a certain temperature to determine what the vapor pressure will be at a second, different temperature. When we meet next week for class, I'll do at least one example with the Clausius-Clapeyron equation, since it might be a little bit mathematically intimidating if you've never seen it before. This slide gives us some experimentally determined vapor pressures for water at different. To put the data in a form that matches the Clausius-Clapeyron equation, we can take the natural log of each pressure value, and to each temperature value we can invert them, or basically take 1 and divide it by the temperature. Plotting these on a graph, we get the following results. A direct plot of temperature versus vapor pressure gives us a quasi-exponential relationship. Plotting the vapor pressure curve for water alongside those of two other liquids, ethanol and ether, shows that this graph shape is consistent between different liquids. After all, they follow the same equation, just with different enthalpies of vaporization. Plotting natural log of the vapor pressure versus 1 over temperature, we observe the straight line plot that you would expect based on the previous slide. The slope is negative due to the negative sign in the leading term of the Clausius-Clapeyron equation in front of the enthalpy of vaporization. Now that we've analyzed vaporization, the transition from liquid to gas, let's talk about some other phase changes. With 3 phases of matter, there are 6 different ways to transition from one phase into a different phase, otherwise known as a phase change or a state change. Each of these has their own terminology. Moving from the solid state to the liquid state is commonly known as melting, although the term used for the associated enthalpy change is generally fusion. Vaporization, as we just saw, is the transition from liquid to gas. One you might be less familiar with is sublimation, where a solid transitions directly into the gas phase without passing through the liquid phase. If you've ever played with dry ice pellets, which are frozen carbon dioxide, you may actually have witnessed this phenomenon. Dry ice evaporates directly from the solid state without ever melting. The reverse of each of these processes also have their own terms. Freezing, of course, is what happens when a liquid becomes a solid. Just think of liquid water freezing into ice cubes. A gas that becomes a liquid is said to have undergone condensation, just like the condensation that builds up on, say, a window when water vapor forms drops of liquid on its surface. Finally, the opposite of sublimation, moving directly from gas to solid without becoming a liquid, is known as deposition. This diagram shows us what's going on with these phase changes in thermodynamic terms. Positions lower down on the chart correspond to lower enthalpy and entropy. If you've not come across the notion of entropy before, you can think of it as a measure of disorder in a system. Solids have low entropy because they tend to consist of atoms, ions, or molecules held rigidly in place in an ordered or repeating framework. Liquids have comparatively higher entropy than solids, as the molecules in liquids are still close together, but they can move past each other much more freely. Gases have much higher entropy than liquids or solids do, as the molecules are essentially completely independent of each other, moving in random straight-line paths. For any phase change that involves moving from a lower entropy phase to a higher entropy one, the enthalpy change will be positive or endothermic. This is because, for instance, in a melting solid, energy from the surroundings has to be absorbed to give the molecules enough energy to overcome some of the intermolecular forces locking them into place in the solid. Likewise, when a liquid boils, it needs to absorb a relatively large amount of energy so that the molecules will be moving fast enough to overcome their intermolecular interactions and have enough energy to escape into the gas phase. The exact opposite is true of phase changes from higher to lower entropy states. For example, a gas condensing to a liquid or a liquid freezing into a solid. All of those processes will have negative enthalpy values, so they'll be exothermic. A few other things to notice here. Because enthalpy is a state function, all phase changes that are opposite of each other have the exact opposite thermodynamic changes. For instance, water has an enthalpy of vaporization of about 40 kilojoules per mole positive. So we know that its enthalpy of condensation must be the same size but with the opposite sign, so negative 40 kilojoules per mole. Also arising from the fact that enthalpy is a state function, meaning that it only depends on the initial and final states of the system and not the path taken along the way, is that the enthalpy of sublimation, for instance, is just equal to the combined enthalpies of fusion and vaporization. For instance, water has an enthalpy of fusion of about 6 kilojoules per mole, so its enthalpy of sublimation will be those 6 kilojoules per mole plus the 40 kilojoules per mole from the vaporization to give us 46 kilojoules per mole for sublimation. One last note on this chart, it does do a good job of getting the general idea across, but it makes it seem like the entropy of a liquid is about halfway between that of a solid and a gas. In reality, the vast majority of substances have a pretty small difference in entropy between the solid and liquid states, and a much larger entropy difference between the liquid and gas states. So, quantitatively, the liquid state should be much closer to the bottom of the chart as opposed to right in the middle.